Hello, my name is Jeffrey Hesler. I'm from Virginia Diodes, and I'm going to talk today about THz test and measurement equipment, and particularly with a focus on wideband communications, things like 5G and 6G. Traditionally, the kind of main technology driver for terahertz has been basic science, so fields ranging from astronomy, physics, chemistry, fusion plasma diagnostics. In the upper right, I've shown a photograph of the ALMA radio telescope array. It's a terahertz telescope array on a 5,000 meter plateau in Chile. And this telescope array, the ALMA array, was part of the group that did the image of the black hole, done at 230 gigahertz last year. And so you can see the picture there. However, commercial applications are really starting to take off at terahertz, I think in large part due to the progress that we've seen in the last decade or two in terahertz transistors. Some really amazing rapid progress there with a wide variety of semiconductors from silicon CMOS, SiGe, gallium arsenide, gallium nitride, with terahertz transistors pushing all the way to beyond 1 terahertz. So some really amazing progress in these transistors. And the applications that are starting to kind of really come to the fore, things like concealed weapons detection. I've shown an image of a terahertz security screening system that's being used in the subways in London. This is from a company called ThruVision. So looking through clothing for things like knives or other weapons to keep things safe in the subways in London. So concealed weapons detection, but also weather forecasting, and then the focus today, which is going to be wideband and secure communications. So again, 5G and 6G. 6G, kind of a little fuzzy exactly where what frequency ranges this will be since it's a bit early, but let's say communications above 100 gigahertz. There's been a real strong growth over the past year or so in these 100 plus gigahertz communication links with, and for evidence of that, I've shown kind of some screen grabs of just some typical things I found on the internet with some large companies and quite a wide variety of countries, all really touting 6G research and really trying to push this along even at this early stage before 5G is really even fully rolled out. Some of the proposed applications are things like micro to macro cell backhaul, events, things like sporting events or concerts, ports for like shipping type ports or airports, and fiber closure, and then kind of a wide variety of other applications as well. The World Radio Communication Conference held at the end of 2019. At that conference, there were discussions of fixed and mobile allocations all the way up to 450 gigahertz. So this terahertz communication is really starting to happen. Lots of interest and development there. It's clearly in the early stages, and people aren't really talking about product or implementation up until, say, 2030 or something like that. But we'll see. So in order to develop these systems for, say, 6G or these other applications, you need to be able to test and measure components and devices and systems to develop these new applications. Some of the type of devices that need to be tested: package devices, on-wafer devices, differential, over-the-air testing. So, for example, devices with on-chip antennas, these are all going to be very important. There's also a wide variety of testing requirements for these different devices, ranging from S parameters to various nonlinear kind of intermodulation distortion, EVM, IQ measurements, antenna patterns, emission testing. So a real wide variety of test requirements that need to be done to fully develop these systems and components at these high frequencies. These sort of measurements are done routinely at microwave frequencies, microwave to millimeter wave, and so I've shown a series of some of typical measurement instrumentation that is used down at these microwave ranges. So these types of tests are done routinely down at microwave, and so what can we do to extend this measurement equipment up into the terahertz range? So next I'd like to introduce Virginia Diodes, VDI. We're a small high technology company. We really are focused on terahertz technology. That's been our traditional focus, and it is something that is our core technology, really focused on terahertz. We use nonlinear Schottky diodes to extend the frequency range of microwave electronics. So the Schottky diodes I've shown a picture here to the right of one of the devices. These are fabricated at our company. We have a small captive clean room that we use to fabricate our own custom designs for these diodes. These are very low parasitic capacitance, very small devices to enable us to push all the way up to 3 terahertz or even 5 terahertz with these devices. We take these diodes, we mount them into waveguide housings like that's shown here in the lower right. We use waveguide largely because it's a very low loss transmission line medium, or relatively low loss transmission line medium in terahertz, and so it gives us some of the best performance we can do. So we use the nonlinearity of the Schottky diode for frequency conversion, kind of up to and back from the terahertz. So things like frequency multiplication, doublers or triplers, and also frequency mixing, just classic heterodyne type down conversion. So combining kind of this microwave instrumentation with this Schottky diode nonlinear kind of waveguide based technology allows us to then extend that instrumentation into the terahertz range and enable the type of measurements that were done at microwaves into this terahertz region. So as one example, this is a signal generator extender, so taking a low frequency, say below 20 gigahertz synthesizer and extending this up into the terahertz range. So we combine a series of amplifiers and multipliers down at, say, microwaves to millimeter waves, and then a series of terahertz multipliers to extend this up into the terahertz range. And I've shown down below a signal generator and then one of these signal generator extenders here attached to the unit. These are just turnkey sources, tunerless, so just instantaneous sweeping over the waveguide band. And we have standard units up to 1.1 terahertz. And to give one example, this is a WR 3.4 system, 220 to 330 gigahertz, output power 6 to 8 dBm over much of the band. And so very high output power levels and to generate signals up at terahertz. A slightly more complex instrument, the vector network analyzer, where we can extend kind of the classic S-parameter measurement and compression, load pull type measurements that are done at microwaves with VNAs, extend these into the terahertz range. These include things, we have dual source modules, which can allow you to do, say, differential measurements or TOI or IP3 measurements. We have VNA extenders available now up to 1.5 terahertz with very high test port power and dynamic range. So, for example, 120 dB dynamic range is typical up to 500 gigahertz. I've shown performance for a WR 6.5 VNA extender covering the 110 to 170 gigahertz range. Test port power 13 dBm typical, peaking around 15 or 16 dBm, and again dynamic range at 120 dB. One of the things, these our extenders are quite compact in form factor, and that's quite a key enabling technology when we look at doing on-wafer testing, something obviously that we worked quite a bit on with form factor. So I've shown an example here on the right of a long waveguide run connecting an extender down to the probe and down to the device under test under the microscope here. And you've got microscope things which kind of make it difficult. The interferences perhaps limit you to moving your extender in close and reducing this loss. And so these compact extenders, you can see an example here where form factor has now kind of optimized the system to reduce these losses, move this extender in very close to the device under test, and increase the test performance. So this helps not only with the kind of general measurement quality, but also enables you to take this high test port power that we have available and deliver this down to the wafer so that you can test devices, look at compression of these nonlinear devices on wafer and over temperature. Regarding these type of compression measurements, there's test port power leveling built into the VNA. So you can look at small signal testing or compression testing of the devices. And so I'm going to give an example quickly of load pull and compression testing. This is work done by Maury at Maury Microwave using VDI frequency extenders. These you can see the frequency extenders here. This is going to be an active load pull type measurement, and so in the images here they're measuring a 125 gigahertz HBT silicon germanium. You can see gain compression curves versus RF power, PAE, and then down in the right looking at load pull type measurements for covering looking at the performance as a function of the output impedance. And again, this high output power is important for being able to cover a larger range of the impedances with your measurement. Next, go ahead and focus on spectrum analyzer extenders. So taking spectrum analyzers, allowing you to measure signal purity, phase noise. We use low order mixers, which allows us to have very high signal sensitivity. And so you can use these for things like noise figure testing. We have these analyzer extenders available up to 1.1 terahertz. These have very wide IF bandwidths and very low displayed average noise level, or DANL, minus 150 dBm to 750 gigahertz, minus 135 dBm per hertz, all the way up to 1.1 terahertz. So again, very low noise figure on these devices. Also, we have made these in a compact form factor, so you can attach these onto probe stations or onto, say, robotic arms for over-the-air testing chambers, and so keeping them kind of lightweight to allow faster scanning and to allow you to use less expensive motors. So next I'll talk about terahertz wideband signal generation and detection. For digital communications, wideband signals are kind of are everything. People want to put lots of information into a certain frequency and very efficient, and so looking at complex modulation scheme, things like OFDM or QAM, and so you've got these complex banded signals, and where these channel bandwidths can be quite wide, usually a few gigahertz, but people now very interested in 10 gigahertz or even much wider channel bandwidths. Traditional frequency multipliers, so the signal generator extenders I described earlier, they can generate very high power, but they distort wideband signals. That's basically frequency modulation or multiplication is essentially a phase multiplication, and you also have a nonlinear amplitude transfer function which distorts amplitude modulation. So in order to be able to both generate and detect these wideband signals, we've developed a series of compact up and down converters where we've really focused on reducing distortion and intermodulation for these signals to get the best EVM performance and the best signal-to-noise ratios. So this is an example of a millimeter wave signal generation system for these wideband type signals. So we take a compact up converter, which is really one of these mixers used to upconvert. It's got a local oscillator signal here that we will feed in from a signal generator down, typically again 20 gigahertz or maybe up to 40-50 gigahertz, depending on the application. And then into the IF of the mixer, we feed in a wideband signal generator, an arbitrary waveform generator, or something like that. Feed in some sort of complex modulated signal. So that then gets upconverted into the millimeter wave. And so we're now in the millimeter wave, but generally for our upconverters, these are double sideband upconversions, so you end up with basically an upper sideband and a lower sideband copy of the signal. For some applications that's fine, but in many cases people would like to, say, focus only on the upper sideband part and eliminate the lower sideband part. So we've developed a series of bandpass filters that we can then use to clean up this millimeter wave signal. So the bandpass filters, I've shown an example here. These are waveguide based components, classic kind of filter type design, multi-pole irises, machined in waveguide. And then we use these type filters to remove unwanted sidebands, to also block, say, LO leakage. These filters, one of the reasons we use waveguides, we get this very low passband insertion loss, and you can kind of see that these are actually measured filter performance here, not simulations. We get very high out-of-band rejection, sharp skirts, and we have these type of filters available at a variety of bands, all the way up to a few hundred gigahertz for bands that are being considered for 5G and 6G. And we've even developed a filter up at 600 gigahertz, although that was more for scientific application, not for communications yet. So with the bandpass filter, we can kind of clean up the signal, end up with a nice copy of this input complicated waveform, now up at millimeter waves. But in this conversion process, we've lost some of the signal power, so there's a conversion efficiency for this upconversion. Not much loss, but there's a little bit loss in the bandpass filter. Feed that in, and so we've now got this clean signal, but at a lower amplitude than we'd like. So we go ahead and we need to amplify that signal. And so we've been doing a lot of work to develop amplifiers up to 250 gigahertz to use in generating these broadband modulated signals. We're using these new state-of-the-art indium phosphide transistors from Teledyne. It's a 250 nanometer indium phosphide HBT technology, and you can see one of the chips here on the upper right. At VDI, we've worked to package these very efficiently and we're able to achieve performance very similar to the On-Wafer, and so very low loss type packaging, and really maintaining the quality of the MMIC chip itself, even though we're packaged. We have these amplifiers covering waveguide bands from WR15 all the way up to WR4, so 170 to 250 gigahertz. These typically have full waveguide band coverage, quite reasonable gain and saturated output power. So for example, 20 dBm at WR12 to about 16 dBm at WR4, and I've shown an example of an amplifier at WR6.5 to the right here, the gain of 20 dB, typical, about 18 dBm PSAT, that's shown here. So we can then use that amplifier to boost the signal power of this modulated signal, and now we've got a good, clean terahertz copy of this modulated signal, which we can then use to look at simulated radio, to analyze some sort of device out in the field, do channel sounding, a wide variety of applications. So this is one example of this. This was a 140 gigahertz communication link demo that was shown at the Brooklyn 5G Summit in 2019. In this case, there was a 4 gigahertz wide input signal, where that input signal was sent in from 4 to 8 gigahertz, and so we generated this wideband signal from 140 to 144 gigahertz, with both bandpass filtering and amplification, similar to what I just showed. And this is being used by Ted Rappaport's group at NYU for doing channel sounding. This is some work done by Keysight using the VDI compact up and down converters. And so you can see here's a case where you've got a wide variety of microwave and millimeter wave test equipment here, from arbitrary waveform generators, signal generators, oscilloscope, data analysis on computer using the VSA software from Keysight. And then these are being up and down converted into the millimeter waves using the these VDI extenders that I've mentioned before. And so you can see here, up converter, amplifier, this is a variable attenuator, and then down converter here. So this is an example of a simulated radio measurement using the D-band 110 to 170 gigahertz up and down converters. You can see the 16 QAM signal here in the figure to the right, about a 4.3 gigahertz channel bandwidth, an EVM of 2.1% was measured for this, so very good low distortion of these signals, and similar quality of signals were generated up to even 64 QAM. Here's another example, extreme bandwidth with 10 gigahertz of occupied bandwidth, a 16 QAM signal. You can start to see things drifting a little bit here, but still 4.7% EVM, and they were able to achieve good performance up to 128 QAM with this. So to summarize, THz technology, it's an emerging field, long history in basic science, but a lot of really exciting new things in commercial applications being developed now. Our focus at Virginia Diodes is to be able to test and measure these so that you can develop better components at these frequencies. The kind of millimeter wave testing takeaways, you can leverage existing equipment. A lot of the old microwave equipment can be just extended up. You want to use true mixers, low order mixers, not high harmonic mixers, so you can get this good noise performance. Cable loss is very important. You really want to put your probe near the device under test to avoid all of these losses. You want small form factor, and high dynamic range really does affect things. So we'll end there, and thank you very much, and I appreciate your attention.